morning, students. In this session, we are going to see what is multi-level queue scheduling and also multi-level feedback queue scheduling. In the previous sessions, we have discussed the process scheduling algorithms where we have discussed about FCFS, SJF, non-preemption, preemption, priority and round robin. So apart from all these 4 process scheduling algorithms, we also extend the scheduling algorithms to multi-level queuing scheduling. Myself, Dr. Shirisha, Associate Professor, MLR Institute of Technology, CSC Department. So what is multi-level queue scheduling? So when you are executing few processes, there are few processes which run in the foreground and there are few processes which will run in the background. So to manage all these processes, we introduce this multi-level queuing scheduling where we have multiple ready queues, and based on these ready queues, one after the other sequentially, if there are 3 ready queues, say Q0, Q1, Q2, so sequentially Q0 will complete its process, say Q0 is there and Q1 is there, Q2 is there, and there's a ready queue. This is ready queue for Q1, Q0, and there is a ready queue for Q2. So when you have such and there are queues, then what happens is there once the processes which are resided in this queue will complete their execution, then later on this next process will complete, next ready queue will complete and next ready queue will complete. Like that we are differentiating the ready queues and followed by we are giving them as multi-level queuing scheduling. So how this works, we'll see. Ready queue is partitioned into separate queues, as I told you, separate queues. So where, for example, you have all the foreground processes which are interactive. Interactive is like where you want responses from the server, where you are giving the input and where you are getting the output. Like you will be interactive with the process that you have between the user and the kernel. And the batch process is where which runs in the background and the response time is little large. Response time will be larger, means maximum. Okay, so these are few processes that we can differentiate. So process permanently is given in the queue. So if there are n processes, say P1 to P10, there will be a interactive process, and these will be in the ready queue 1, ready queue 0, and P11 to say P20 there are batch processes, and we will put these in the other queue which are in the ready queue 1. So when this is the case, each queue has its own scheduling algorithm. So here in the multi-level queuing, mostly we will be using the foreground process will be using RR, which is nothing but your round robin scheduling algorithm. Similarly, when you are executing the process which are residing in the background, so the background process can run using the scheduling algorithm which is first come, first serve. So these are the 2 scheduling algorithms. Scheduling must be done between the queues. So we got 2 queues here. So one ready queue 1 will undergo its process to execute their job. After completion of all these processes, then Q1 will get a opportunity. So scheduling must be done between the queues. So how this scheduling can be done is we have fixed priority scheduling. Fixed priority scheduling here means all the interactive process will have the higher priority when compared to your batch process which are having the lower priority. So all the higher priority process will be executed first. So fixed priority scheduling is serve all the foreground then from the background. That means what? All the interactive process or the foreground process will be having the highest priority. Therefore, all the process residing in that queue will be executed first. So possibility of starvation. Why there is a possibility of starvation? Because when you are executing all the interactive process, foreground process, then what about this background process? They have to wait. So they will be waiting for a longer period of time until all the foreground process will complete their job. So longer waiting period is nothing but starvation. So starvation means what? Longer waiting time. Okay. Now, time slice. Time slice is where you give the time slice for a process so that the process can execute only for that particular time period, and it will give the chance for the rest of the process. So time slice, each queue gets a certain amount of CPU time which can schedule among its process, that is 80% to foregrounds in the RR. So whatever the foreground process are given, so all the process should get a chance for their execution. So how it is getting a chance? By using this round robin scheduling. So foreground process mostly are given round robin to schedule their jobs to avoid starvation between the process, and 20% to the background process in the FCFS, because FCFS is given to the background process as the response time is very maximum, means longer response time will be there. So to avoid a starvation among the interactive process which are having the higher priority, we are giving 20% to the background of the background process which can be executed by the FCFS, first come first serve. So this is about a multi-level queuing where multiple scheduling algorithms together we are using in between the ready queues. So this is where we are having the diagram for multi-level queuing, where these are the different set of process. Say first process is divided into system process, where the response time is very less response time is required. Okay, and you have interactive process, where these interactive process will have higher response time. So interactive editing process also belongs to higher response time again. So like that you have. So whenever there is a less response time, the process which are having the less response time will lie into the system process, and they will be having the highest priority. So when there are highest priority for all these processes, say P1 to P10 are lying under this, all these P10 process will be executed using which algorithm? That is a round robin algorithm. So you'll apply the round robin, give the time slices where you are avoiding the starvation problem. Okay, now, and after executing the system process, completion of all these processes, then all the process will come out of the system process as their jobs are completed. Now next there will be next queue. This is, say this is Q0, this is Q1. After completion of all the process which are having a highest priority here, next it will go to the next highest priority process. So they are nothing but the interactive process. So these interactive process are also having the highest priority than interactive batch and student process, whereas having a less priority process for less priority than the system process. So after executing Q0, all the process in the Q1 will undergo its execution. Therefore here also mostly will be using a round robin scheduling algorithms. So wherever there are interactive, we are using a round robin, but the sequence of the process that are going to the execution may be varying because of their high priorities. Next is the batch process. Batch process is a higher response time again. When there is a highest response time, so here we may use FCFS, where FCFS gives response time will be higher because all the process one after the other they have to complete their executions. Even though the burst times are lower or higher, according to the burst times, the complete program or the complete process should execute, then only the next process can execute. That is about the batch process. And student process, or the process which are not in the system process, we are calling them as a student process, and these processes are also executing in terms of FCFS. The 20% of the importance is given to this lowest priority process, as these are having a lower priority. So batch process and the student process will be having a lower priority than compared to the interactive process. So this diagram depicts how many different types of process are there, and based on the priorities, we are executing this multi-level queue scheduling algorithms. Then, what is multi-level feedback queue? So, multi-level queuing, as we have seen, there are multiple queues based upon the response times and the priorities. You are executing two different processes, either round robin or the CFS algorithms based on the requirement. So, 20% importance is given to the batch process or the student process, and 80% importance is given to the round robin algorithm, where you can implement them for the interactive process. So what is this feedback queuing is to avoid the starvation problem. So what is happening there in terms of batch process or student process, the waiting time will be much longer. So it again leads to the starvation in between the queues. Okay, so that's why it is named as multi-level queue. And that to overcome that problem, a process can move between the various queues. So that we are calling this as a multi-level feedback queuing. Feedback queuing and go to the process, make the priorities high and get it into the execution. So that is process can move between the various queue, and aging can be implemented this way. What is aging? Whatever the process which are having lower priority, say P3 and P4 having lower priorities and they are been waiting for a longer period of time, then what we do, we increase these priorities, so that these can undergo the execution, so that you are avoiding what? Starvation. Avoid the starvation. So this type of process where you are increasing the priorities and getting into the execution, that process we are calling it as aging. So multi-level feedback queue schedule are defined by the following parameters. So we'll have to know what are the number of queues you have, what are the scheduling algorithms of each queue, and method used to determine when to upgrade a process. Upgrade means what? Giving the priorities. And method used to determine when to demote a process. So whenever there is some IO or when there is an interrupt in the process, then until that IO operation is performed or that interrupt is overcome, that process has to wait. So whenever the process is waiting, the CPU will become idle. So when the CPU is becoming idle, there is no responsiveness, right? So to demote means what? You are swapping out that process from the current processor. Therefore, the other process which are having the higher priorities than that can undergo into the execution during that period of time until the IO waiting period is completed. So that is the method. Next one. And the method used to determine which queue a process will enter when that process needs service. So all these steps or all these parameters should be taken care by the multi-level feedback queue scheduling. We'll see a small diagram where we have three queues here. So we have Q0 and we have Q1, Q2, and see that there are three queues. And Q0 is indicating what? RR. What is RR? Round robin. So we have a round robin algorithm with a time quantum of 8 milliseconds. So what is the time quantum? So time quantum or time slice both are same in the round robin algorithm. If you want what is round robin and how it works, you can go to the previous session where round robin is discussed. So when Q0 is given, when Q0 queue is having a set of process and they are having a quantum equal to 8. So the process which are lower than the burst times of those processes which are lower than 8, so will come under this queuing, Q0. And the process which are having 16 milliseconds round robin, those processes will lie under Q1. And those processes which are having a least priority can go to Q2. So in that way, we are classifying Q0, Q1 and Q2 based upon their burst times and the time slices. And after completion of all these Q1 processes, when they are out, then only the queuing will go back to the next quantum or the next queuing, ready queue, and which is Q1, and it will undergo all the process. After completion of all these process, then only it will go for the next queue, which is of Q2. Then Q2 will undergo all its process. So like this, what is happening is, these are the process which are having the highest priority. Therefore, we are implementing what? Round robin algorithm. And this is the process with the lowest priority. Okay. Then a new job enters the queue, which is served as FCFS. When it gains the CPU, job receives at 8 milliseconds. If it does not finish in 8 milliseconds, this job is moved to the Q1. So if it is not executed in the 8 milliseconds, then we are increasing the quantum. The time quantum is more here. Therefore, we are moving this from Q0 to Q1. Now, what is happening in that case? Nowhere the processor will be in the idle state. The processor will always in the execution state of where the less responsive time is there. So all the process can be resided in the Q1, and we are moving all the process which are having higher response time to Q1 and Q2 later on according to the requirement. So that is where a new job enters the Q1 and which is served as FCFS. And at Q1 job is again served FCFS and receives 16 additional milliseconds. So here we have additional 16 milliseconds. If it still does not complete, then what we have to do? We have to send it to FCFS, because if you are executing more than 16 milliseconds here, there is a quantum. So quantum will not allow you to execute after 16. So when it is coming to 17, it stops and it demotes the process. It deallocates that address location and it gives the process to the next queue where it has to execute it has to serve as a FCFS. So here we are using a multi-level process scheduling algorithms, and your queuing diagram, we are moving the process between the queues. So therefore, we are calling this as a multi-level feedback queue. And this moving of process in between the queues is not possible in the multi-level queuing. Therefore, there are two algorithms we have divided: multi-level queuing diagram and multi-level feedback queue. And what are threads? So with the multi-level queue and multi-level feedback, we have completed all the process scheduling algorithms. We move on to the threads under process. So to introduce a notion of thread, a fundamental unit of CPU utilization that forms a basis of multi-threaded computer system. So a thread is nothing but a lightweight process. So when you wanted to do some task, so you divide them into different modules, and each thread, so if you have a single thread, then it will execute only that single thread and the CPU will go to the idle state. So we are moving from single thread to multi-threaded computing. So because whenever a single thread has completed its job, it has to go to the second thread and execute its job. So to move from one thread to other, we are using a context switches where the switching is possible, and once switching is possible, the context switch the scheduler or the dispatcher goes to the next process and it dispatches the process to the scheduler. So when the second process is coming, the CPU is now, it is not idle, the second process is executing. So in that way, we are introducing this multi-threaded computer system. So all the applications which you are using today are all multi-threaded, and threads run within the application, and multiple tasks within the application can be implemented as a separate task. So when you are using different functions or different functions you are doing, different activities you are doing, each activity we can call it as a single thread. For example, update the display, fetching data, spell checking, answering network requests. So these are all different activities that we are doing. So everything we can call it as a thread. Process creation is heavyweight, while thread creation is a lightweight. So process creation is a combination of multiple threads, where it is again heavyweight, and thread is a lightweight. Can simplify the code and increase the efficiency. And kernels are generally multi-threaded. Even the kernel view or the user view, we have two different modes of operations. So in the user perspective or in the kernel perspective, when the process or threads are under execution, they have to be multiple threads should be executed at a given period of time. If it is not so, the processor will undergo idle state. Whenever the process is undergoing idle state, the efficiency decreases, the performance decreases. Okay, the aim of these process synchronizations or process scheduling algorithms, everything is to improve the efficiency and improve the performance of different processors, right? So for which we need multi-threaded programming. So here we have a multi-threaded server architecture where we have a client who is sending a request to the server. Whenever a request is sent to the server, it resumes listening for additional client requests. Whenever one request is over, it will serve as a thread and it will complete its job. Whenever it has been completed, now the server will be idle and it will be listening for all the threads which are being again the requests are getting from the client or not. So to check that, it will send few system calls and it will bind all the system call is used to collect all the requests. Therefore, the server will collect all the requests and send back to the processor for its execution. So here every request is creating a new thread to service that request. So what are the benefits of this threading? There are different benefits where you implement this multi-threading. So high responsiveness may allow continued execution if the part of process is blocked. So whenever the process is blocked, you are not allowing the processor to be idle until it is unblocked. You are making the blocked process to terminate and you are giving the chance for the other process. So especially important for user interfaces. And the second one is a resource sharing where the multiple resources can be connected to one processor and threads share the resources of the processes easier than the shared memory or message passing. So in the message passing, we know that there will be a one-to-one communication, end-to-end communication, whereas in the shared memory, one-to-many communication can be happen, because one will be the writer and the other all will be the readers. So that is how the resource sharing is possible in the IPC mechanism. The threads also share the resources and it is easier than these IPC mechanisms. And economy. So when you use thread, it is cheaper than the process creation. Thread switching lower overhead than the context switching. So thread switching means one thread to other thread, you can switch very easily because thread is a lightweight process. So as the thread switching is very lower overhead, we are calling this thread as execution of thread as a lightweight process. Scalability. Process can take advantage of multiprocessor architecture. So multiprocessors can also implement this client server with the multiple threads. Whenever you are getting a new request, it is acting as a new thread. So this may happen in a single processor or even multiple processors are also increase, so that we call this can achieve the scalability when you are using multi-threaded programming. So those are the some advantages we have seen, and moving further we'll see what are the different types of threads. So we have single and multi-threaded process. So when you are talking about a single thread process, there is only a single thread, maybe the execution of a small code. Okay, so when you are executing a single thread, so it is divided into a different, the entire program you are calling it as a code, and where in that code if you have any global variables, okay, then where those variable values can be globally accessed, so that you can call it as a data. Okay, and files which are open, so whatever the files which are open for execution of particular thread, so all that will be resided in the files. And registers is where you use to store the data. So you store the data in the form of register and you use the stack to place all the registers and to access the registers in the LIFO fashion. So stack is used for that. So a single thread, whenever it is wanted to execute some code, it can execute that process, and after its execution again CPU will go to the idle state. Whenever this is into the idle state, again there is whatever the benefits we have seen, like responsiveness, scalability and efficiency and all. So all that will be degraded. So to avoid that, we are moving from single threaded to multi-threaded. Whenever this is blocked, say this is blocked, so whenever this is blocked, this will go for its execution. It will not wait until this is unblocked. We are giving chance to the other process. Therefore, there is a high response time and also the performance will be upgraded. So here we are using different registers and stacks, and we are using the same complete program as a code, and its variables or its functions or whatever parameters you are passing as a data, and all the files related to that will be resided in the files. So multiple threads can also possible in today's applications, whatever we are using, all are multi-threaded only. So this is about a single thread and multi-thread. We'll see in the multi-threaded what are the user threads and what is kernel threads and how many different types are there. So user threads, they are managed by the user level threads library. So three primary thread libraries are there. So POSIX threads, that is a P thread, and Windows and Java threads. According to the operating system we are using, a Linux or Unix operating system, we are calling them as a POSIX P threads. And in Windows, what are the threads we use? So those are window threads, and Java threads where we are using a JVM. And kernel threads which are supported by the operating system, that's a kernel. So the example for which we can use these user threads and kernel threads will be all these operating system supports this threads. Okay. And what are multi-threaded models is, in the multi-threader there may be many to one model and one to one model and many to many. What is this many to one? There will be many user threads and there will be one kernel thread. Okay, there will be one to one. So there will be one user thread and one kernel thread. There will be more user threads and more kernel threads. So all these are possible when we are discussing about multi-threaded programming. So these are the few models we have. So when it is coming to many to one model, the first type of model, there will be many user threads. So you have multiple user threads. So wherever this thread will execute, parallelly you are executing other threads also. But how many kernel threads you have? Only one. So this is one and this is n. Therefore we are calling it as many to one. And one thread blocking causes all to block. So here user threads, one thread if it is blocked, it is blocking, because only that kernel has to use is the center point where you have this kernel thread. This has to execute all the user. If this is blocked, what happens? All the user threads will be under hold. It will block all the threads. So multiple threads may not run in parallel on the multi-core system, because only one may be in the kernel at a time. So how many kernel threads are there? Only one. What if this is failed? So all the user threads will be blocked. So this is a drawback of this many to one. And the examples for this will be Solaris green threads and GNU portable threads. And we'll move to one, where you have only one user thread and one kernel thread. So even though this kernel is blocked, only one thread is blocked here, whereas other kernel threads will execute other user threads. So that's the advantage of many to one. Drawback can be overcome in the one to one. So each user level thread maps to the kernel thread. Each user level thread is mapped to kernel thread. Creating a user level thread creates a kernel thread and more concurrency than many to one, because parallelly you have several other threads which are executing. Number of threads per process sometimes restricted due to the overhead. So number of threads per process, one process, how many threads should be there, so that sometimes you may restrict them, because if you are increasing the number of threads, what happens is there will be a longer overhead and there will be some interrupts or higher the response time. So what we are doing, we are decreasing the number of threads that can be restricted sometimes. So examples, Windows, Linux and Solaris. And whatever the operating systems that are up to means upgraded after this can also be supporting this. And what is many to many model? Allow many user level threads to be mapped to multiple kernel level threads. You have many user threads, there are 4 user threads and there are 3 kernel threads. Allow the operating system to create sufficient number of kernel threads. Therefore, every user process will have some other kernel thread for its execution. Even though this is blocked, these kernel threads can handle those user threads, because all are connected together. So the many to one is only having the drawback where you are using only one kernel thread, where it blocks all the user threads if the one kernel thread is blocked. So that drawback is overcome in one to one and also in the many to many model. So we have Windows with thread fiber package where it can support this many to many model, and Solaris version 9, before version 9, can support this many to many models. And there is a 2-level model where we have many to many, similar to many to many. So except that it allows user thread to be bound to kernel thread. So all the user threads are bounded to the kernel. Bounded means what? Limit. There will be a limit of how many user level threads should be connected to the kernel thread. So these are the few examples that we have where we can see 2 levels. So there's a single level and there is a multi-level. So different levels are there here. These are the 2-level model. And many to many model, as we have seen, it supports multiple threads, but they are bounded, and here also we are using bounding. So these are the different types of threads, and we have seen about multi-level queue and multi-level feedback queue scheduling. Hope you all understood. Thank you all.